In this chapter, we will be focusing on another spectroscopic method called nuclear magnetic resonance spectroscopy, or NMR. We'll go over some general information, and then we will focus on proton NMR, followed by carbon-13 NMR, and then we'll talk just briefly about some other NMR techniques. We've already talked about other types of spectroscopy, in particular infrared spectroscopy, which gives us information on bond types and functional groups. But we've also been talking about reactions. One reaction of an alkene gives an alcohol. Now, because we are adding a hydrogen and an OH across the double bond, it is possible that the hydrogen becomes connected here and the OH here, which gives this product, or that the hydrogen becomes connected here and the OH becomes connected here, giving this product. Now, these two compounds would look very similar by IR spectroscopy. In both cases, we would see the sp3 hybridized carbons connected to hydrogens, we would see an alcohol OH, and we would see a carbon-oxygen bond as well. IR wouldn't be very useful to be able to determine which regiochemistry we obtained. Unlike IR, NMR spectroscopy can give very specific information about the carbon skeleton, which would enable us to distinguish between these two compounds. Proton NMR can give information on the types of hydrogens that are in a molecule. What is their environment? Are they next to polar groups? How many neighbors are there? And then the C13 NMR can give information on the specific C13 environment as well. So there's a lot of information that can be obtained. So we will focus on understanding nuclear magnetic resonance spectroscopy. Now, before we get into the details of proton NMR spectroscopy, I want to skip ahead so that you can see what information can be obtained from a proton NMR spectrum. So this is skipping ahead, but let's see what we can do. So here we have a proton NMR spectrum. Here we have our axis, and then we have signals or peaks that are rising up. And additional information we have is that this compound has the molecular formula C4H8O2. Now, in general, with a proton NMR spectrum, there are 4 types of information that can be gleaned from the spectrum. One is based on the number of signals. This gives us information on the distinct types of hydrogens. So for this spectrum, this is a signal made up of 4 peaks, this is a signal, and this is a signal. So that tells us that we have 3 sets of hydrogens. Another important piece of information is the chemical shift. This is called delta. And although it's not written on here, the units are ppm, or parts per million. And the chemical shift gives us information on the environment around the different sets of hydrogens. In other words, it tells us what types of hydrogens we have present. So this signal, if we look at the center, this has a chemical shift of about 4.3 ppm. And based on my understanding of NMR and knowing a little bit of information about the molecular formula, I know that this signal at about 4.3 ppm, this is most likely a hydrogen connected to a carbon that is connected to an oxygen. This signal at about 2.4 ppm, this is probably a hydrogen connected to a carbon that is connected to a carbonyl. And then this signal at about 1.9 ppm, this is most likely a hydrogen connected to a regular sp3 hybridized carbon that's further removed from anything special. So it's kind of a typical CH. The third piece of information is the integration. Now, integration gives us information on the number of hydrogens that give rise to a particular signal. Now, the integration might be represented on spectra in different ways. On this one, this is the integral. So think about this from your math class where the integral symbol looks like this. And what we're looking at then is the distance from the top to the bottom. So for this particular signal, it's made up of 4 peaks. So this integral is adding up the area underneath the first peak, the second peak, the third peak, and the fourth peak. And so this distance, this height, is what we are interested in. The second integral is this one right here. And then the third integral, or the integral for the third signal, is here. So we are comparing the height of this integral with the height of this integral and the height of this integral. And so for this particular spectrum, the integration tells us that there is a ratio of 2 to 3 to 3. So if 2 hydrogens give rise to this signal, then there are 3 hydrogens that give rise to this signal and 3 hydrogens that give rise to this signal. That gives us, in this case, a total of 8 hydrogens, which is what we have in our molecular formula. The fourth piece of information that we can get from a proton NMR spectrum is the splitting. The splitting can be seen in the appearance of the signal. So this is a signal that is a single peak, whereas this signal is made up of 3 peaks with a particular height ratio. And then this signal is made up of 4 peaks, again, with distinct height differences among the different peaks. Now, splitting gives information not on the hydrogen itself or set of hydrogens, but it gives information on how many hydrogen neighbors there are. So for this first signal, because there are 4 peaks, that tells us that the hydrogens that give rise to the signal have 3 hydrogen neighbors. For the second signal, this is a singlet, so that means that the hydrogens that give rise to the signal have 0 neighbors. And then the third signal, we have a triplet. There are 3 peaks, so that tells us that the hydrogens that give rise to this signal have 2 neighbors. So that's the information that can be determined from the splitting. Now, if we put all of this information together, along with the molecular formula, we can determine the structure of the compound that gives rise to this spectrum. So we have a CH3 group connected to a C double bond O, connected to an O, CH2, CH3. Now, if we call this signal A, that corresponds to this set of hydrogens. They appear at 4.3 ppm because they are next to an oxygen. They integrate to 2 hydrogens because they have 2 hydrogens. And they appear as a quartet because they have 3 hydrogen neighbors. And that's what we see here are the 3 hydrogen neighbors. This signal, let's call this one signal B, that corresponds to these hydrogens. This absorbs around 2.4 ppm because it is hydrogens connected to a carbon that's connected to a carbonyl, and it integrates to 3 hydrogens because it's 3 hydrogens, and it has 0 neighbors because adjacent is a carbon that doesn't have any hydrogens connected to it. And then finally, if we call this one signal C, this corresponds to signal C. It's kind of a typical set of hydrogens. They're connected to an sp3 hybridized carbon. They're a little bit further removed from the oxygen. These are a fairly typical set of hydrogens. They integrate to 3 hydrogens because this is a CH3, and it appears as a triplet because it has 2 neighbors. So this CH3 group has 2 hydrogen neighbors adjacent to it. So this proton NMR spectrum corresponds to this structure. Now, this was the preview. This is where we are going. We're going to spend the next several class periods, the next couple videos, looking at the details of the number of signals, looking at the details of chemical shift and integration and splitting. We'll be looking at a structure and predicting what the spectrum is going to look like. But eventually, we're going to be able to, as we did here, we're going to be able to look at the spectrum and determine the corresponding structure.